if you want to go ahead and advance. I don't have. So the Society for the Advancement of Chicanos and Hispanics Native Americans in Science is a national organization. It is dedicated to making science more inclusive and accessible to all people. And with that, oh, I think your screen just awesome. And with that, it comes the National SACNAS Conference. I don't know if we have advancement ability on the slide. Oh, thank you. But the National Science or the National Diversity in STEM Conference is the National SACNAS Conference. Its registration is open, and it's currently being held, or it's going to be held this year in Columbus, Ohio, from October 30th to November 1st. Registration is currently open, and if you are interested in
Thank you, thank you. Thank you for that awesome introduction, Zeta. Thank you to the SACNAS chapter at UCSD for inviting me to present today. And thank you to the students who are watching and participating via Zoom or in person there at UCSD. I know it's been a eventful 2 days. The whole schedule has been really interesting to see on Instagram, virtually on this side. It looks like it's been chock full of a lot of lessons and learnings. And so I'm just happy to add to that timeline for today. Today's presentation, hopefully you leave with some knowledge about not only science communication and why it's super important for the time we are in now, but overall in general in life. We need to always be communicating science effectively. It's a way for us to definitely get away from misinformation. We need to know where we get our science from and who to trust in terms of getting our knowledge. And of course, this is more relevant now than ever. But yeah, hopefully we get into some of that. I also want to leave with you some practical skills. This session in particular has been supported by a really great group of folks. One representative I have here today that I hope to introduce you guys today. This is from the Rosetta community, but it's a specific company that has actually supported our learning today, our practical hands-on learning for protein design. It's a company called Levitate Bio. I cannot wait to introduce Karen Carr, who will come on here today to not only share about Levitate Bio and how we'll be utilizing it today, but also a brief story of her journey and career in science. We also have some students who are tuning in, not only at UCSD, at the SACNIS chapter there, but we also have some students from my alma maters, University of Washington, shout out UW, as well as Claflin University in Orangeburg, South Carolina. Both of these schools have students who will be participating as well in the hands-on protein design workshop that we have here. I know you guys are probably watching on YouTube or on Twitch or X, so please do comment so that we see y'all in the chat and make sure that things are going well. Hey, we are in 2025. If the chat is not involved, are you really online? Right? But yeah, let me jump a little bit into about myself so that you guys know a little bit about me. So let me go ahead and share my screen with you. Here we go. And let's go slideshow. Make sure this is sharing as well. And please do let me know at any point in time if you can't hear me so that we make sure that you can hear me at all times. Share screen. Do you see these slides? Andrea? Okay, perfect. Yes. So yeah, quick introduction to me as a scientist and just like my career path so far. Yeah, I did my bachelor's in science and biology. I think a lot of the stuff is relevant to talk about just because students early on, particularly students from underrepresented minority communities, kind of are told that there's just a one path to becoming a scientist, when indeed the path to becoming a scientist is as myriad as, you know, the winding rivers of our world, right? There are many different opportunities in science, and there are many ways to get to those different positions in science. So I just love to share my journey just so that others know that it's not just one path, it's multiple. But yeah, I got my bachelor's from Claflin University. This is a historically Black college in Orangeburg, South Carolina. I focus specifically in biology. And in fact, I started research during that time in Dr. Panasik's lab, specifically on enzymes. I was fascinated by enzymes at an early age, but at that time, I didn't know how do you apply research in a actual day-to-day world, you know, like what kind of careers do you utilize with research outside of being, you know, a professor or a doctor. And so I decided to actually apply for a post-baccalaureate program. This was at a company in Boston, Massachusetts. It's called Novartis Institute for Biomedical Research. They had this program called a post-baccalaureate program. Many other companies have these types of programs. They're called PrEP programs. NIH actually offers one as well. So do other universities like Duke University. They offer these kind of programs. These programs essentially are there to beta test grad school. Grad school is about 6 years average of your life. And so these programs are there to help students really kind of, test out whether they can commit, you know, that time to that 6 years to grad school. And that's what I got to do at Novartis. I was in the oncology department. I did assay development during my time there and really got to talk to other scientists, career scientists, PhD scientists who were doing the stuff that I would do in a PhD program. I matriculated out of that program in 2014. And by the end of that program, I'd already applied to grad school. So it was also a nice 2 years that I used to apply to grad schools, like different grad schools. Made sure that I also did my GREs, you know, before applying to grad schools. Got recommendation letters also from, you know, the scientists that I was working with, as well as previous scientists, all while working in 9 to 5 and actually getting a feel of what the job would look like after I get, my PhD. And so, yeah, so during that time I applied, and there were other students in that cohort who were applying for MD positions. Some people are MD, PhD, some people were thinking of masters in like global health programs. This was the time really to explore. And so by the time I left there, I had decided to go to University of Washington, specifically because of David Baker. During my time at Novartis, I had realized that proteins, not only are they good in a theoretical sense, like, enzymes that I was studying during my research internships and programs at Claflin, but also in a real world drug discovery settings. Proteins seem to be the node of drug discovery, whether it's, the assays that I was developing there in the oncology department, or just even seeing from fellow scientists' projects how, in cell signaling pathways, a protein is typically the central node of all developmental pipelines. And so I was like, okay, I'm really fascinated in this, and I really want to learn more about how do proteins fold. And then, I actually ended up discovering that you can actually make your own proteins, right, from scratch. De novo design, which is a field that has now gained quite a lot of popularity by my mentor there at University of Washington, David Baker. So yeah, I did my 5 years there as a graduate student. This was in the biophysics and protein design program. This was at University of Washington in Seattle. And yeah, I started off as a wet lab scientist. So started off basically at the bench, right? Mixing chemicals, doing the assay development stuff, but actually learned there's another side to science that I actually did gravitate towards, which is coding on the computer, dry lab portion, right? There's a mix of bioinformatics and coding that is at the center of protein design, where you get to not only understand the folding pathways of these different proteins, but you also now get to engineer your own protein utilizing that information. And you do that through, whatever myriad of ways now. In 2025, there's a myriad of ways. At that time, Rosetta was the program that was, gold standard really within the world. And this program allowed you to basically code brand new proteins from scratch, but also allowed you to understand natural proteins from the very basis. And so during my time until 2019, when I graduated, I focused on a specific class of proteins. These are called beta sheet type proteins. These beta sheet proteins are really at the center of a lot of enzymes, a lot of antibodies. These are made up of these beta sheet type proteins. And it's really a topology or a subdivision of a class of proteins. You can have mixed alpha beta proteins, you can have all alpha proteins, you can have beta proteins. I was really fascinated by particularly all beta proteins. Just at that time, it was a challenge that in the world, at that time, there was not really a de novo all beta protein. And so it's something I wanted to understand. Why are they so difficult to design? And then in understanding the design, you also understand the biology, right? The folding, understand how these proteins actually come to be well folded. If you can design a protein, then you probably understand the mechanisms that are involved in it folding into a full protein. And then 2020, the pandemic happened. I stayed on as a postdoc at what was now the Institute for Protein Design. And I decided to take the lessons that we'd learned from the 5 years I was there, focusing on these, super, challenging folds, which are all beta folds called jelly roll folds, which are super non-local, which is the most challenging fold that you can imagine. I decided to focus those learnings that we'd learned from there to something a bit more simpler, but within the same scope, which is immunoglobulin proteins, super local, a bunch of hairpins, honestly, but also very relevant because they are the topologies that make up antibodies, for instance, that fight against diseases in your body, right? And so applying the same lessons to now designing de novo these type of proteins. And so within about 6 months of starting as a postdoc, that's when the pandemic hit. I decided to stay on as an essential worker. And the nice thing was during this time also, a lot of the AI-based methods were also coming out of the Baker Lab. And so I got to get involved with people like Yvonne and Sergey, as well as Sam Pellock, in some of these early hallucination protocols, and actually got to design my own proteins during that time. And so it was quite early on when I realized that AI already had an impact in biochemistry. You know, not only did I realize it was going to be a force in 2020, but we already knew that it was here because we were playing around with these tools and seeing how remarkably better AI was able to design de novo proteins faster and more accurate in some cases than our traditional Rosetta methods, which were, you know, based on biophysics principles. And so it was really a fascinating time during 2020, but also a really stressful time, as you can imagine. And so by the end of 2020, I decided to look for a position as a group leader, and I decided to look back at Novartis, which was my former company, but this time in San Diego. I applied for a position there, and they were looking for somebody exactly that, who would not only lead a group, but also design proteins in a drug discovery pipeline, right? So yeah, I started there actually at the end of 2020, like December, and started growing a team for about 3 years. I was there in San Diego as part of the biotherapeutics group. And during this time, I really got to see not only the evolution of the field, right? As AI was really taking over in many different fields, it was really dominating within the space. In protein design, and getting to see that and having a front row access in drug discovery in a huge company like Novartis was very thrilling, very amazing. And all the while, I really wanted to make sure that I also teach about protein design. You know, one thing I didn't mention was that in the beginning of my time with David Baker, I was his first Black graduate student to graduate, you know? And so I knew that people from my community did not have access to these tools, did not know what protein design was. When I would talk about protein design online or to my parents, they'd be like, what? You're making molecules from scratch? What does that mean? You know? And knowing how impactful these lessons are, these skills are, and knowing how lucrative financially they are to a community, I took it upon myself to make sure that at least my community was in the loop, would be aware of this stuff. And so even right after I graduated 2019, I started, my small little science communication company to really not only communicate at the time my thesis or what I'm doing to folks that are in my community, but it started growing into a much larger focus. Really, as the more I did science communication, the more I realized that when communities do not have scientists that graduate in those areas, problems that affect those communities go without scientific solutions, right? And then even more, misinformation festers within those communities and affects them even more. And so I realized, okay, this is a big need, and not only just joined the rest of the science communication community in talking about science, but I decided to do it in a unique way, in a way that was true to form to how I was matriculating throughout my career. And so, yeah, I'll talk a little bit about Stimulator, which is the science communication company that evolved out of all of this, and that I kind of decided in 2023 to focus solely on as I left Novartis. Yeah. Today, I am speaking to SACNAS, right? Society for Advancement of Chicanos and Native Americans in Science. And you might think, I would not be the typical speaker at SACNAS, but having been a part of SACNAS since 2010, I know there are so many areas in which we align. We, outside of the dominant culture, shared perspectives with like lived experiences that rhyme with each other. So even though my, origins are not of Hispanic nature or Latino, I do know that I am outside of the dominant culture. And so there are a lot of rhymes and reasons that share. It's a community with many polyglots, people who speak multiple languages. My second language is Shona. And so oftentimes I find community with that. I'm also an immigrant in the United States. It's a unique experience that is different, right? For most people in America. And so I find a lot of community also with a lot of either immigrants or people who have immigrant families or immigrant friends within the community. And I've been here since 2009 through multiple different types of visas and green cards and all the sorts. And so I know the journey that it takes also to live a life here is quite unique. And I found quite a lot of community within SACNAS in struggles within all of these different things, all in the pursuit of science, which is the beautiful thing. Most SACNAS members that I've met are either the first generation to graduate or first generation to be in sciences. A lot of SACNAS folks that I've interacted with at conferences are, really breaking the ceiling within their own families, but also sometimes within their own communities of being the first scientist that is going to find solutions to bring back to their community. I actually looked up in my email, and this is the first interaction that I had with SACNAS all the way back in 2010. It was a SACNAS competition in a SACNAS conference in Anaheim, California. So yeah, I've loved this organization for a very long time, and have found community and stayed with community here. But yeah, the type of scientist I am is one that identifies disease impacting a patient population with little or no solution. This is where I am now as a principal scientist at a drug discovery startup. Is something that I love doing, is working with a team to identify exactly something like this. I know that proteins, particularly, which are my favorite molecules, are a node in a cell signaling or fundamental pathway, typically, that is at the center of drug discovery. And there's usually some sort of validated activity of that protein that is associated with disease-relevant mutations or with disease-relevant activity. That, to me, is where drug discovery really is. That's why it's a target for drug discovery. Proteins generally are applied to all of these different things, and the most fascinating things for me as a scientist to attack. And I've been doing this for a while now, as not only a scientist working in 9 to 5, but also with the side gig as a science communicator. You, as students, probably might recognize some of these as poster conferences that you have done in the last 2 days. I saw some poster competitions going on. So you already know that science communication is important for a scientist's growth and professional career. To grow as a scientist, you need to be able to talk about your science to a myriad of different type of people, right? Not just to fellow scientists who are working in your specific niche, but you need to be able to talk to potential mentors, to talk to senior scientists who are within your field to get more insights about how to navigate your field. You need to also talk to scientists outside of your field, whether it is to find funding for your science, because especially in these times, we need to be able to communicate our science to be able to get funding. But in general, you need to be able to do that. You need to be able to talk to folks about why your science is important, why your specific area not only requires funding, but requires attention, right? Requires either to recruit more scientists to work on the specific problem that you're working on, or just to at least care about that specific area. And then more broadly, we as underrepresented minorities, we need to talk about our science to our community in a different way, right? A lot of times, if you are a first generation student graduating, or first generation scientist who's even in science, as I was, you need to really talk about science from its very basics, right? You need to talk about why research is important and why our taxes have to go to paying towards this research, because there's a lot of misinformation out there. A lot of people are talking about science, particularly scientific research, in a very harmful way that not only affects funding pipelines, but also affects how people view science careers. The fact that we have very few Black scientists, very few Latino scientists, very few women in science, it is because of a confluence of all of these different events. The fact that we have few scientists, of diverse scientists within the population, impacts directly the image and the perception for young scientists to go into that field, because it almost seems, if you're a young scientist looking to this field, you almost seem like you don't belong, right? And so it's important for us to be visible, communicating our science, showing that we're there to show the next generation that science is happening within our communities, with people who look like us, with people who have our similar backgrounds, in order to also recruit more scientists within that pipeline, right? But also to show that scientists come in many different forms, and it's really science is not really about your background or your personality, right? It's really more about how you think about things logically. It's a field that can be attractive to anybody, right? Yeah. So I'm showing here examples of science communication early on. This is when I was a sophomore and freshman. I spoke to Nobel laureate at that time, Martin Chalfie, together with my advisor at Claflin University, Dr. P, who's actually, I think, on this call. So shout out Dr. P for early introduction into research. And so that was my beginnings. This is more recent with Stimulator. What I've been able to do is start this science communication company that uses pop culture and social media to discuss protein design specifically. You will find out today in the workshop, the hands-on that we're doing today, but also in a little bit of what I said, that protein design actually involves all 5 of the elements that are involved in STEAM, science. Obviously, it's a life science field, biochemistry in particular, technology. We're using computers and algorithms every single day to do prediction as well as design, as you will see today. It's an engineering element because we are modifying native proteins, or in the case of de novo design, we're actually engineering brand new proteins that have never existed before to address new solutions that or new problems that are popping up today. There's definitely an artistic element in protein design. Speak to any protein designer, and I am so happy you have one on the call today, other than myself as well. You will hear that there is an artistic element about looking at the different structures. Because structure informs function, there is an inherent artistic nature in protein design. And then lastly, math. Math runs all of our different algorithms. Like I mentioned, there is a coding element within protein design. And so, yeah, I really thought the Stimulator moniker was perfect for who I am as a scientist and who I am as a protein designer. But I also wanted to use this popularity that particularly my community has with hip hop, right? Hip hop is the #1 genre in many places you go. And so I wanted to fuse those 2 elements to bring enthusiasm into biochemistry, which I have seen. I've seen since I started in June 2019. I have been associating with many different communities through using my courses like hip hop biochemistry or Stimulator games. I have been able to get celebrities to even take notice. Nick Cannon, who I'm showing right here, actually invited me on his radio show to learn more about protein and protein design. He even sponsored a season that we did during that time. So it was on Amazon's platform called AMP. I started a radio show where folks would actually call in and compete almost survivor style about designing proteins. And these were people from all walks of nature. All of 18 and above is usually my target audience because I really want to have people retain in college and start a lot of these more advanced skill sets. And I believe a lot of people are talking to younger than 18-year-old children, but I think we have a retention problem. So my main audience is really 18 and above, but they were either stay-at-home mothers, they were people who either used to love science and fell out of love with science but joined in. It was all different people, and in fact a few of our students who participated in the earlier seasons of Stimulator games where they designed their own proteins actually presented at conferences. So I'm showing on the right here 2 of my students, Kamara Ice and Amma Nicole, who actually presented posters at Abercrombie's competition. Both of them community college students, first time conference, and then they went to an international conference like Abercrombie's in 2023, presenting some of this work. And throughout all of this, more eyes also kind of came upon what we were doing. We have shout outs from people like Nicki Minaj, who's saying Stimulator on stream and live. Also, even companies like PBS. This is a live stream that we did with Nova PBS as well as STEM Media, who I was invited on there in their informal educational learning experience to actually start bringing a lot of not only this science communication to a wider audience, but even to do it in a more practical sense and try to bring it on a PBS network, a wide, broad network. So this is what we've been doing so far. And to me, it really stems from right here, from community, from SACNAS, the people who are viewing right now, Claflin University, UW. Like, community is an opportunity to give back, right? It's a way to teach about protein design, teach about what we're doing, but also I think we find strength in the intersectionality that is within our community. This is an article I wrote in 2021 where I even described, how we have oppression from all of these different identities that we have, with a woman in STEM, it's very few women in STEM, very few Black people in STEM, very few Latinas or Latinos in STEM. And you might feel the weight of that. And you especially I felt it matriculating throughout. There's something called imposter syndrome that almost every scientist faces, but there's a unique case of imposter syndrome that comes from being a minority in STEM. And I found the biggest solution for me was embracing my intersectionality. The fact that I speak, multiple languages, and the stuff that I talked about with SACNAS allowed me to find community with SACNAS. The fact that, I was a Black student allowed me to find community in places like Abercamps, right, dedicated to minoritized and marginalized students. The fact that, I did understand that struggle of being one of a few in a room, that allowed me to, to really understand some of the struggles that women in science go through, right? And so I even went to Grace Hopper conferences and really found friendships within that. So the more intersectionality that I found within myself, the more community I was able to find. And this is something that I, give as advice to young scientists, is to really embrace all aspects of your identity and bring your whole self to your science. That way, you also are able to embrace the multiple different communities that you can be involved in. And community really is the bedrock of how to survive a lot of different things. But yeah, so I've talked a lot about myself and my discipline, and I've given some trailers and teasers about how you're going to learn about protein design today in a brief hands-on workshop that you will be able to take away and be able to continue on for about, I think it's about a week or a month. I will verify with Karen, but today you will get some of the very few basics of protein design. And why learn protein design? If I haven't said it enough, because we are very proud of this moment, but the 2024 prize last year, half of it went to David Baker for de novo protein design. So this is a field that is recognized not only in Times, because he was also Times, one of the 100 times important people, is a field that's recognized internationally by the Nobel Prize community, but it's also something that is affecting not startups that have started just based on protein design. So it's also a very lucrative area. And when we're talking about lucrative areas, jobs, there are jobs targeted towards protein design folks. One of the things that people I've heard throughout my journeys about science, people think there is no money in science. And, while the news right now kind of can imply that a little bit, the honest truth is that scientists, particularly PhD scientists working within a lot of these fields, are able to earn quite a lot of money, six-figure jobs within protein design, doing things that you love. And so there are quite a few jobs, right, especially right now with the Nobel Prize. I think this is a very important skill to have. If it's something that it's interesting to you at all, I think it's a very important skill to harness and apply. Internships right now, I know students who are listening right now might be gearing up to start thinking about what fields that they want to apply to or what jobs they want to do. Having some internships early on really gives you that opportunity to, not only gain skills, but also practice those skills, practice some of your theoretical understanding that you've been learning in your classes, also get experience for you to start applying for those jobs, and experience also to know whether you like it, right? Like sometimes you really, the only way to know whether you like doing something or I wouldn't say capable, because I think anyone is capable of protein design, honestly. But I think if it's nice to like what you do. And so internships give you that small window of like, oh, this is something I like. And hopefully our Karen can talk a little bit about some of the internships that actually are available with the Rosetta group. Rosetta Commons group. And then lastly, there are many protein design competitions that have exploded now recently. One example I'm giving right here is, of course, there's the Stimulator Games. Our protein design competition is now on its fourth season, where we've given $1,000 to a student every single season who has participated in this $1,000 cash, right? But there are other protein design competitions, some sponsored by NIH, some by private companies. I'm highlighting here this Align is a non-profit organization that is been organizing this protein engineering competition. They are now on their second round, and it's open to the public. Anyone can participate. The last round was actually published, so the people who participated are actually now authors on a paper. Getting authorships on paper is also great for your grad school application, for your professional growth. So it's an opportunity. Adaptive is another competition, protein design competition. I'm not showing here, but it's another protein design competition organized by a company, a literal company, that actually opens it up to more people. And I do believe more and more of this is going to happen. Protein design is a very open science community, an open science discipline. So today we will be focusing on a very similar, protein design competition, right? We're utilizing simulator games as the forum to actually start learning this. And this is sort of a kickoff. So you will not be an expert after today, but you will have the tools necessary for you to garner an interest. And this is facilitated by our sponsor who have graciously donated credits for every student who wants to participate. At the beginning of this call today, you should have gotten an email to the email you used to RSVP with instructions on how to secure your $200 bag, okay, for free worth of credits to use in Levitate Bio's bench platform. This allows you to do protein design using some of the state-of-the-art techniques that are out here, utilizing AI that we've been talking about so far. So I'm just showing here a quick screenshot. If you click the link that I sent you in your email, you'll be able to subscribe, the $200 per month feature. Put in the code that you've been given there, try bench. That's right here, try bench. That's right here. And that $200 you'll see go straight to zero. Okay. Which means you don't have to pay $200 today to learn some of these awesome things thanks to Levitate Bio. And then you'll be able to sign up, start an account. And from there, we will really get into some of the nitty gritties. And so, yeah, without further ado, I do want to bring on my guest who you might have already kind of heard a little bit about throughout this. Oh, my computer is freezing. Oh no. No. Okay. Oh no. Okay. As this is loading, can I with Andrea? Do you have the email? Did you get the email to sign up? Can you hear me? That's a good question. Okay, I will do that. Let's do that. I'll do that during the presentation just now. If you did not get the link to sign up, make sure to check out the YouTube screen. I'll put a link right there so that you can sign up now. But about 40 people, I think, who had signed up through the RSVP got an email today. But okay, thank you for that confirmation. So yeah, we'll share the link as well. And I'll share it in the Zoom here so that people also have access to it as a clickable link. Because it is only for a month. So, so yeah. But I want to introduce, without further ado, one of my speakers today, who's going to come on, Karen Carr, who began her career as a doctor of chiropractic, earning her DC from Cleveland Chiropractic College and practicing throughout her 30s. Driven by a growing interest in biomedical research, she returned to school and completed a PhD in computational biology at the University of Kansas, working in the Nicholas lab on structure-based drug design. So from 2018 to 2024, she was a computational biologist at Cyrus Biotechnology, which is a spin-out from David Baker Group, where she contributed to the development of advanced protein modeling software. In 2024, the software division of Cyrus spun out to form what is now Levitate Bio, where Karen now continues her work at the intersection of AI and protein design, and is a VIP. So let's welcome Karen to the stage. Hi, Karen. Yes, yes, we're so happy to have you. And thank you again for donating these credits to our students to practice protein design. But yeah, I know you had some slides prepared, so please take it away. Andrea, can you give access? Stop sharing. Okay, I can do that. Yes, we can.
All right. So this is just my LinkedIn. So this is, I'm a EVP of Sales and Business Development, which doesn't sound very sciencey, but when you're running a software, a protein modeling software company, that's where it goes. So let me just describe my scientific journey as to how I came here. So as Muck described, I was a chiropractor back in the day. But I didn't find it very satisfying. I needed something very much more like scientific. And so I made the stupid decision to go back to school, which was economically a horrible idea. So I took some classes in research, and I really fell in love and found that's the thing I should be doing with my life. So I started a master's then at University of Missouri in Kansas City. I was expecting to do my PhD there, and so I was in the Yoder and Wyckoff lab working on comparative genomics. And that's really when I discovered the joy of computational biology. So I had done a little bit of like computer engineering when I was in high school, but when I went to college, it didn't seem like a very welcoming community for the ladies. So that would be back in 1990 when 99% of the people in the computer classes were men. So it didn't occur to me that I should continue my enjoyment of software engineering. So I went another route, but then once I was exposed to some computational biology, I really enjoyed that data analysis and that being able to like process through data and then discover something scientifically out of it. So I worked in comparative genomics. So we were looking at positive evolution, and I really enjoyed that. So, but I wasn't really getting the support I wanted there. So I made another stupid decision, is to drop out of that PhD program and find a PhD program that had more computational support. So this was a lot of wet lab people at UMKC. So I went to a computational biology department specifically. And that's where I joined the Carinniculus lab and got my PhD there. And the Carinniculus lab just happened to be focusing on the Rosetta molecular modeling suite. So that's where I learned how cool Rosetta is. I went to my very first Rosetta conference that summer. And the Rosetta community is this like big consortium of amazing scientists that it's 110 labs now that all work. They have conferences 3 times a year, East Coast, West Coast, and Europe. I think there's supposed to be one in South America now. It's all very, it's a great community. So so here is actually the picture of the Rosetta Con last summer. So you can see me over in the corner here. So this is just like 200 people. A different mix comes every year. It's just a good supportive environment. They're each using these computational biology tools to model proteins. In the Carinniculus lab, where I got my PhD, I focused on modeling proteins to find small molecule docking sites. So I learned a lot of that, like the computational tools you have in Rosetta, because it's this deep, elaborate set of protocols, but they're being written by a bunch of different labs. So it's kind of hard to figure out how to do each individual thing. So you really need a lab to support you and learn all that. So when I graduated, I was thinking of doing a postdoc But I was really excited to hear about Cyrus Biotechnology, so I joined them. And the reason I was super excited to join them is because they automate a lot of these Rosetta protocols to make them easy to use. And so that's the Cyrus Bench platform, which you guys have access to today. So I joined them. So here's a little description of Cyrus and my current company, Levitate. So Cyrus started in 2015 as a spin out of the Baker Lab. They automated Rosetta protocols on a nice online GUI, so you can just access that in a web browser like you're doing now. And so you don't need to have a PhD in a Rosetta lab, and we provide full training and support. So it's starting to sound like an ad, yeah. But anyway, so it's my job at Cyrus was just to help decide what tools would be added and figure out the best way to talk to customers about what they're doing, to develop documentation to support their work, talk to customers and help them work with that. And Cyrus also did a lot of fee-for-service work for customers. So I got to talk to a lot of customers about what kind of projects they do. And these were mostly pharmaceutical companies that are creating protein-based therapeutics. And so it was really nice to hear like what the industry is doing, and also agriculture and synthetic biology, people creating new exciting ways to create enzymes to eat sewage waste or create alternate forms of energy. It was just really cool to see what commercial spaces are doing. So I had been exposed to a lot of academic labs through the Rosetta community, and the academics are all about creating something new, and commercial space is all about using what exists for practical purposes. And I kind of like that more. So Cyrus was doing a lot of fee-for-service work. So their board decided that they should focus completely on that, because the board wanted them to make they thought they had more potential that way. And so they stopped working on the software development. So then that allowed us at Levitate to spin out with their original goal. So that's what we do now. And so we automate those tools for use at companies. So now my job at this new spin out is to continue that original goal. And now I'm EVP of sales and business development. So now I'm in a position that's, I'm technically a salesperson, but I still do the same thing. I talk to customers about what their science is, and that's just super exciting to me to, like right now, I'm speaking to you from Boston. I'm normally based in Seattle. So I'm at this protein engineering conference all week and just getting to hear all of the really cool stuff that people are doing. So I've really loved that. And the software that you're using today is the bench software, which is the push button versions. And you'll see our documentation online will help you understand what those tools are. And when we work with customers, we'll usually do an online training. So we get to talk to them what their goals and help them figure out what tool is best for them. I'm sure Mook will walk you through what your goals are here today. And so like from my scientific journey perspective, I bounced around a lot just trying to find the thing that spoke to me. I was really lucky to have support. The thing I wish I knew when I was in the 90s, when I was working on my bachelor's, I wish I'd known that if you'd gone to grad school, they pay your tuition and give you a stipend, because I think like that was a surprise to me. So that when you're working on your PhD, you're working in a lab, and so you get a lot of support, and it's not great wages, but you're not going into debt, and so that's super great, and that definitely provides more opportunity, and it's that's certainly the challenges of the world today. Is everyone has so much student debt. It's nice to be able to skip that component of it as well. And there's just a lot of opportunities once you get a PhD, or if you just get a master's in biology. I know the current administration is making huge cuts, but and this is out of the ordinary, but the science is always a cycle like this. There are always high times and low times, and the high times will come back. And if you progress definitely happens, and if you're at the undergrad level now, there will be opportunities in the future to come. So I definitely hope people will stick with it. Speaking of opportunities, the Rosetta Commons is a really great organization that is a nonprofit that organizes the Rosetta community, the 110 labs. They support workshops and they support the conferences, and there's this really great group or opportunity for undergrads for you to get some from research experience. So they've been doing this for a super long time. It's a program that happens every summer. It starts mid-June. It goes to mid-August. The first week you go to a Rosetta workshop. So you just all hang out together and just learn the basics of how to use Rosetta. And today there's classic Rosetta where you're doing a physics-based calculations of proteins and sampling dynamics and sampling mutations one at a time. And then there's the fancy AI approaches, and it's kind of amazing how much things have changed in that space in the last 5 years. And so then there's 8 weeks in which you are working in a specific Rosetta lab, and there's 20 Rosetta labs currently participating, and that includes David Baker's lab in Seattle, and really all over the world now. There's a lot like Germany and North Carolina. And at the very end, you get to go to the RosettaCon, where you get a full week of posters and talks, and you'll hopefully have a poster of yourself to show off. And so this is something where applications usually open up in November, and they give you a stipend, so you have something to live on and travel and stuff like that. So I highly recommend that. And hopefully I'll see you guys at a RosettaCon if you join this experience. And so if you go to rosettacommons.org, there is an education link there, and this research experience for undergraduates can be found there. So that's the basics of what I was going to share, and I'm happy to help with the software for when you're testing the software, if you have any questions during that process.
This is great. Thank you. Thank you so much, Karen. And it's so good to hear your journey in science, because, you know, different journeys happen in science to get to the end. Yeah. And it's so nice to hear you in Boston. I hope I get a chance to meet up with you briefly. When you're also here in Boston.
We're swapping coasts. Yeah.
So yeah, I do have some questions for the Levitate Bio. I know folks are probably scrambling to sign up right now and create their accounts. For the students, they will have access to this for a month, right?
Yes, yeah. So it's 30 days of access, and we limit that because most people are commercial companies, and people can use Rosetta free for 30 days to try it. But actually, academics can use it as long as they want. But our implementation is limited to 30 days. But we can always, if people want to try a little more, we can fudge it. So.
Awesome. All right. Well, thank you again for your presentation. And again, I cannot thank you enough for giving access to the students to actually be able to play around with the software. But without further ado, we shall begin that. But I feel like the students have heard a little bit of a journey that leads to industry. I thought maybe perhaps I could bring on my former professor, Dr. Panasic, to come on and talk a little bit about his journey in science. Dr. P, are you there? I see you're in the Zoom. Let's see if you unmute.
Give me just a second here to switch cameras.
Oh, awesome. Yeah, we can hear you though. That's good. While that's happening, students, if you've already received your link, well, let's start. If you haven't received your link, check the Zoom chat. There is a link there. And if not, then check the youtube.com/stimulator where we're live streaming right now. You see there's a link on the front screen, and the link is simply levitate.bio/subscribe. When you get there, the landing page it looks like this. Let me see if I can share this. Yeah, I'll share this. The landing page looks like this, where you can sign up for $200. You'll be able to sign up, but instead you put in your code TryBench, and using that code TryBench, you will be able to get this for $0. And so you can see right there for a month. So TryBench, $0. And once you're in, it will automatically send you instructions on how to your username is the email that you use to sign in, but you know how to generate a password so that you can do future sign-ins. And immediately it gives you also some of the information for the support materials that Karen was mentioning earlier on, support and documentation about the different programs that you could play around with. AlphaFold, which is a super big AI protein structure prediction based program that also, I think the other half of the Nobel Prize is also available to play around with in Levitate Bio, so you can play around with there. And several other tools that we will talk about even at the end of today. But definitely check out that. In that email, it's a very detailed email. It's about 6 different prompts that allow you to get access to that. The very important thing would be after you get that email, make sure to reset your password so that you have a new password that you can use to sign up now and in the future. And that might be in the spam. So check your spam email, because that when you go to forget password, sometimes it's in the spam. So check your spam email and you'll be able to see where you can go back and log in with your actual email and a new password that you would have set up. And once you're in, you'll be able to see Levitate, which looks like this. So I think I'm sharing it on the screen. Dr. P, are you here? Okay, yeah. We'll go into the workshop after, yeah. After.
I think it's going to allow us to ask questions we never could ask before, questions at scale. Instead of looking at a single protein, we can be looking at pathways and all sorts of stuff. And so it's a great time to get into how some of this is done, because there's a lot more development to come. The next 10, 15 years are going to be phenomenal growth in ways that people can't predict. And so it's very easy to be a part of it. So long as you get in now, there's all sorts of pathways. And I think it's been brought up on how many different pathways there are to get into science as there are different people. I'm originally from Chicago, and I went off to University of Wisconsin-Madison because I liked a girl and I was interested in that. And I ended up in a fantastic lab doing protein science, Ron Rains's lab, and it gave me exposure to protein folding and all of these things which I'd known about but never really appreciated. And when you're in that kind of environment with other people who are really smarter than you in a lot of cases, working on all these interesting problems, and you're sitting around and slugging it out side by side, it's just a really neat environment. So much so that by the time I was done, instead of going off for PhD school, I went and actually worked for a pharmaceutical company doing new drug design for a couple of years. And that was an eye-opening experience. It's a completely different world, especially when it comes to supplies in the lab. Also the motivations, because there's always kind of a profit motive there. I think they hired me because they liked the experience I had with organic chemistry. So those students out there that are, still in the slog of things, organic can give you a lot of skills that other folks don't have that can kind of make you marketable if that's something that appeals to you. But then from there it was on to PhD school, and I had the unique opportunity to have two different kinds of PIs, one in crystallography and another one in cold active enzymes. And so it really, the more you can be multidisciplinary, again, the more options that you have, to kind of flower. And from there, it was to Johns Hopkins and doing computational stuff. And so now my lab does the whole thing from wet work to computational stuff. And it really couldn't have succeeded without Dr. Mook here. While he was there, I think he generated somewhere over 400 mutants. We're still analyzing some of them. It's absolutely phenomenal work. And what you're doing here is great. So thanks a lot.
Thank you, Dr. B. Full of flattery, honestly. Thank you. I appreciate that. And thank you for sharing a bit of your trajectory within science and how you're now at Claflin University. Dr. P is one of the most famous professors at Claflin University. Even today, he implements some innovative tools and teaching aids. This is where I got some of my creativity teaching. You will actually hear from a lot of the students at Claflin University that, recording your lectures, for instance, is something unique that Dr. Panasic does and allows you to talk about your science in a way that resonates even when you record back your lectures. So thank you for a lot of the lessons that I gained at Claflin University, including my love for proteins. It really did come from you. Thank you so much, Dr. P. And thank you for joining us today. Appreciate that. All right. And you guys, if you do not know Claflin University, that is the view that Dr. Panasic is showing in the end. We're a small institution. It's about 2,000 students. So we're very mighty about our pride, okay? We're very boastful about our pride, and it's quite beautiful, and we like to show it off for sure, as you can see here. And so, yeah. But yeah, I'm going to start sharing now my bench. Let's see, share this tab as well. Yeah, so I've already created my account the way that you guys will do as well. And make sure I'm sharing it here. And so what I'm going to do is just do a little work. Thank you for that. Thank you so much. So yeah, the tribe bench and the code and the link, everything that is available today, and it is for today. Please, students, sign in today. This is obviously a for-profit company, okay, you guys? So a lot of people are trying to get a lot of this technology. I'm telling you, this is state-of-the-art technology that people are using not only for academic learnings, but you've already heard from Karen, this is also stuff that is being used at companies. And so people would jump on this and, and want to get use of this. So please, if you are planning to participate in this now in the future, please sign up today so that you actually get in and use that code TRIBENCH to secure that $200. Okay, so yeah, at some point, I guess what we're saying is that will not be effective. If you wait tomorrow or a week, that will not be effective. And so don't come crying to me when it's not effective. Okay, sounds good. Okay. Oh yeah, because it's also the weekend coming up. So yeah, make sure to do that now. Or wait till Monday. Yeah. But yeah, if you can see my screen, it looks like you can. I'm on the dashboard right now, and I'm about to. So basically, when you log in, you will see an option to be able to look at projects, and there will be a new CAD project. CAD is computer aided design or discovery design, I think. Computer aided design, which is what protein design is in general, honestly. And so once you go in there, you'll be able to open a new project. You can give it any name that you want. I gave mine SACNAS. Shout out to the University of California, San Diego, SACNAS workshop, which we're at here today. And then it opens up to this view that we're looking at right now. You can already see my name up top. I'm signed in. If you log out, you see all these nice buttons, shiny buttons that we will talk a little bit about. And you also have the documentation associated within your email once you sign up. But I want to draw your attention over here to the left, which is where we begin our journey, first with loading a structure, right? So we already talked about how proteins are fundamental molecules that do all kinds of processes, from the saliva in your mouth that catalyzes carbohydrates, breaks them down to glucose so that you have energy, to antibodies that fight against diseases. The reason why your blood is red is hemoglobin. It's a protein that shuttles around oxygen around, but it also utilizes iron, which is why it is red. So proteins mediate quite a lot of different biological processes. This is why they're super important. And we know that their shape or their structure is directly tied to their function. So understanding the shape of a protein and knowing the shape of the protein is a super important field. In fact, the field is called structural biology. And manipulating that shape, right, that structure, is now where we're talking about protein design, right? Or structure aided design, or other different names, but protein design. So structure loader allows you to load a protein either from your computer. So you can upload a file here from your computer. My students from Simulator Games Season 2 actually have proteins that they made during their season. So they have those PDB files, which is what we call them. You know how you have Excel files, Word doc files. Well, for a protein structure, one of the main files that is used is called a PDB file, and you can upload it. There are other files you can upload, but we just, for the simplicity, we're going to talk about PDBs. And the reason why it's called a PDB is because it's coming from this huge database called the Protein Data Bank or base, but it is a database of where scientists over the years have uploaded structures of proteins that they have discovered is not the right word, but through trial and error, through multiple different ways, X-ray crystallography, NMR, and even up to today now, cryo-EM and other EM forms, people have been able to figure out and solve the structures of proteins that they are interested in. And indeed, even protein designers who have made brand new proteins have been able to also upload the structures of those proteins into this database. And that's why it's called a PDB file, because it's coming from the protein data base. I think it's bank. But so I have a code here, 4-letter code for a protein that I love and near and dear. This is my thesis molecule. This is one that I actually designed together with my longtime collaborator and postdoc mentor, Enrique Marcos, as well as several collaborators who put a lot of effort and time into this. There's a whole paper associated with this specific PDB code. Please check that out. Of course, this was in the lab of Professor David Baker. And so that code is 6E5C. I love talking about this protein. I actually have a physical model of this protein in my office. It would have been great if I have it right here, but I've shown it in several other live streams. But yeah, this is this protein that we de novo designed. It is an all beta protein. This is the one I was talking about earlier on, and was a structural molecule. But again, you can load any protein you want in that PDB file. If you go to Google right now, type in your favorite type of protein, say it's hemoglobin, or the first protein ever that we got a structure of called myoglobin, which is the reason why beef is red, by the way. Myoglobin, if you type myoglobin and then follow that prompt with PDB, the letter code will come as one of the results. And if you just type in that 4-letter code here, you can immediately visualize your protein of interest. And again, it could be literally any protein that's available in the PDB. And if you have it, if it's not available in the PDB, again, you can upload it as one from your file, like my students did. And we have a couple of those protein designs that we can send around through emails and whatnot. So you can also upload those. But yeah, this is a 3D visualizer that's embedded within the Levitate software. Okay, so you can immediately take a look at your protein. So like we said, structure informs function. But now the question is, what informs structure, right? How does nature know to fold a protein into a specific structure? It comes from the sequence. And in fact, there are 4 levels of structure. The first and primary level is the sequence of your protein. Your protein sequence determines how the final 3D protein structure folds, right? And so in season 3 of Simulator Games, we actually associated the sequence of a protein to words on a page, or words in a wrap lyric. Okay, so season 3 was dedicated to my favorite rapper, Nicki Minaj. And so we took different elements and lyrics from Nicki Minaj, clean ones, I promise. They were only clean ones. And we actually converted those lyrics into proteins. And I'm putting quotation marks, right? Because so a sequence that falls into a protein, this is a specific sequence, right? It has to be specific. And you will find out throughout playing around with these different sequences and playing around with AI folding that if you change the order in which a sequence is placed, you're no longer talking about the same protein, right? So this sequence starts, as you can see, it says 1 here, starts with the letter T, T representing threonine, which is an amino acid, okay? And so what we did within that season, and you will see this if you go to stimulator.com/ hip hop biochemistry or simulator.com/games, you'll see we associated every of the 20 naturally occurring amino acids that make a protein fold into a color. And so if you wanted, you could color myoglobin, you could color oxytocin. These are examples that we showed even in the coloring book that we're able to publish based on this, available at stimulator.com/book. And so when you're learning about these amino acids, know that the specific order that they're in, much like the English language, has a specific relevance to the structure as well as ultimately the function. The word tomorrow is spelled exactly as tomorrow with the T, the O, the R, and so forth, right? If you change any of those letters around, you're no longer talking about the word tomorrow. You're now talking about a different word, right? This is where anagrams come from. Similarly, sequence has to be in the specific sequence of that protein for you to be talking about that protein. More importantly, each portion of the sequence forms the secondary structure, forms the second level of the protein structure, right? And so I'm highlighting. I want to highlight here this portion here that is represented here as an arrow. This is called a beta strand, which is a second level of the structure. This portion that I highlighted here corresponds on the sequence to a specific area that is highlighted right here, AEFE, right? And if you keep going, you can highlight more, but I'm just highlighting this specific area. And you can think of that almost as one word within a sentence. If you change the word placement within that sentence, grammatically, maybe your sentence will make sense, or maybe it'll mean something different, but we're no longer talking specifically about that same sentence. And moreover, these words or these secondary structures associate with each other. So you're seeing this one, this other strand that's pointing in the opposite direction. It's actually associating with that first word or beta strand through what's called hydrogen bonding, right? So hydrogen bonds are structuring these two together as the main force. There are other forces that also mediate these processes, but this is the main force that allow these to associate. So this you can think about when we're talking about poetry or rap as almost how punchlines at the very end, right? The beat is associating with the next line, right? There's some sort of association within the paragraph. Otherwise, that stanza won't make sense. If you take them or mix them around, it's not meaning the same thing. It means something different, right? And then overally, they are three-dimensional, now other forces that I was talking about, right? So this strand also interacts with this strand that's pointing across from it, right? And how that is mediated is through other forces like van der Waals forces. This is stuff that you learn in biochemistry. But in this sense, one thing that we want to focus on specifically are the hydrogen bonding elements that are with specific amino acid identities. And so so there are several. We won't get into all of this, okay? But I want you to understand that this is now associating with this in the same way the end of your stanza at the end of the paragraph of a poem associates with the very beginning to kind of bring meaning to the whole thing. And finally, you have a whole protein that's very much like a poem or several bars, okay? That makes sense when you're talking about rap lyrics. So yeah, I want you guys to start on with this. There are other features. So this is just the graphical interface that allows you to kind of play around with these different things that we're talking about. But imagine if you didn't start from a structure. imagine if you started in the opposite sense, right? So I showed you the structure and I showed you how the sequence makes sense with the structure. But what if you started from just the sequence and you didn't know the structure? This is what structure prediction is called. This is the grounds of, AlphaFold, or there are many other softwares that use this. In this case, we're talking about AlphaFold. This is ESM Fold, and you can see at the bottom here. So this first screen that I've just highlighted, when I clicked AI folding on the right-hand side of the tool here, this screen actually allows you to type in a sequence, right? And now you can't just type garbage. It has to be a sequence that obeys the 20 amino acids, natural occurring amino acids, right? And so we know 6 letters are not available in there. This was also a test in season 2 of Stimulator Games, but B, J, Z, X, Q, and O are not allowed. Those 6 are not allowed. They are the code for other other amino acids, but they're not part of the classical natural amino acids. And so right now, as an exercise, if you are looking at your screen right now, you've already logged in, you put in your account, I want you to type your favorite lyric from a song or anywhere, right, that only obeys the protein amino acid language. So you cannot have these 6 letters, okay? Type that in here, in this box that says AI folding, right? So I'm going to put, let's see, can I put Q? So instead of quick brown fox, I'll put ick brown fox. Can I put B? So R W N fox jump. No, can I do that? Can I do that? Over the lazy. Yeah, so we'll start with that. So this allows you, and honestly, what you should do is actually try to find a sequence available at, UniProt, or you can also find the sequence. You could find your favorite sequence as with your favorite PDB, right? After you've searched PDB, say hemoglobin PDB, find your PDB. It will give you the letter code for your structure, but you could also find a FASTA, which is the sequence, the actual sequence that codes into that structure. Type, copy paste that sequence into this dialog box, and it'll be a fun exercise to actually see if the structure you attain here matches the one that's on the PDB. It will, most likely, but it's also a good exercise. And here is where I was saying you could choose the different tools that you use, where ESM Fold is much faster than AlphaFold 2. OpenFold is also an option that is here. And I think from Karen, I think she mentioned to try to use ESM Fold, I think. So I'm going to try that. You could do this with multimer sequences. So you could also change this mode to multimer sequence. So if you're looking at how one protein associates with another protein, it is important to make sure you get this sequencing portion correct. Otherwise, if there are any invalid characters, then it does flag. And so see, it's already flagging my U there as an invalid character. Because again, remember, you cannot have those 6 letters, B, J, O, Q, and Z and X, right? So those 6 ones, it will flag the box red. Those are invalid. I think also if you have a space, it might also be invalid. So no symbols, no spaces. And once you put that in there, you'll be able to put in a run. So you have access to this for a month. I'll be giving you challenges through your emails that I have. Feel free to participate in these challenges. Those who do participate by the end of the month will win the Stimulator Games Challenge. And as I said before, in our first 3 seasons, we gave out cash prizes for each of those 3 seasons. Stay tuned to figure out what prizes we'll give for this specific season. So make sure to pay attention in the next coming weeks. We cannot do all of it today in one session, but I wanted to give you a kickoff for this. So I'm going to run this. But I don't think it would work. Okay, so we will. It might be too short. I think maybe 100 is the minimum on this. But anyway, we'll send some more challenges that are more up to snuff for the workshop. But I wanted you to at least kick off, try out the software, and see if there are any questions. So let's see. Are there any questions from the audience or from the stream? And I can answer those in our last few 7 minutes. I do want y'all to go to the next session. Let's see, in the stream, were there any? Andrea, I don't know if you are there. Can let me know if there are questions in the audience. Oh, I see. Oh no, please go ahead. I'll read the comment afterwards. Please go ahead. Yeah. Okay, thank you so much for that question. And I see, Andrea, your heads up. So we actually have 3 minutes, not 10, not 6 minutes. So yeah, the nice thing about computational skills versus wet lab skills is that really computational skills you can self teach, right? You can really utilize a number of different resources online. There's the free EDX course that's called Intro to Programming. That's an option if you are somebody who likes more supervised learning. You could do that. But really, the best way to learn, its specific language that you want, whether it's Python or Bash, in terms of coding or whatever, is really to have a problem that you want to solve. And grad school does that better than any place that I know. And so my first day in the Bake Lab, I didn't know how to code. I knew maybe how to pull up some directory files, but I didn't know how to write a lot of code. But with the specific problem of, here you go, you need to implement disulfides in the specific protein, right? Now I have a specific problem, and the tools that I need to use, I need to learn on that journey. And so I did that through talking to experienced coders. I had great mentors, Dr. Pasanta, Dr. Rockland, several people that I was able to talk to, but also, just fully opening up Google and just literally how do I write a for loop? How do I learn about Boolean expressions, that kind of stuff, right? And literally developing that as you go. And then also supplementing that with materials, study materials. A lot of the nice thing about what I've learned computer science and coding is a lot of those communities are open access. So they do offer a lot of these on. And now, yes, thank you so much, Dr. P. Actually mentioned something that's awesome. I was still in my frame of mind of 2018 or 19. In 2025, ChatGPT and Claude and all these other AI programs write code for you. You can debug. I do want to say, it's important to learn some of the fundamentals, learn, because it will write a full-on script if you ask it to. But learn, what the script is doing. Learn how to, maybe write your own line of code. But yes, ChatGPT or other mechanisms are a great way. Dr. P, if you want to say something about this, we have a minute left. People should receive it. Okay, thank you. Thank you for that. And it looks like our time is now ending with the Zoom. But Karen just wants to make sure that if you did not get an email today, you might be getting it on Monday. So you can wait till Monday to get it, just to give that as a buffer. But if you listen to any of this part of this talk, got that code, you are now officially in season 4 of Stimulator Games. So hopefully one of you guys win. And hopefully you've also learned something about science career paths from Dr. Panasic as well as Dr. Karen Carr. So thank you both for joining me today here. Thank you, Andrea. Thank you, Zeta. Thank you, SACNAS, UCSD chapter, for inviting me to do this workshop and bring on folks. Thank you so much. Thank you to the students who are at UW and Claflin who are paying attention and who have been participating in this program. Thank you to anyone who's watching on the live stream. And as I always say, maybe in this sign off, I don't know if we have that much time, but I won't see you later. I will steam you later. Thank you. Thank you. Bye. Thank you for tuning in. Thank you. Bye-bye.